Bismillahirrahmanirrahim. Welcome back to my channel. This is going to be an amazing tutorial on GnuRadio. I just came across this amazing tutorial and I've been wanting to do a video for a very long time, but let's just do it. And of course, after following this tutorial, I will be making a proper derivation video for this particular concept that we're about to discuss using GnuRadio. So the concept that we're about to discuss, this concept is basically known as multipath fading. Multipath fading. So as we know in wireless communication, when a signal that is being transmitted from your transmitter, at the receiving end, you will get multiple copies of the same signal because the signal is being reflected, refracted, being scattered, and things like that. You will get different signal strength, and if they get added at the receiving end, constructively, you will get an entire signal. If they get added destructively, you won't get any signal. This is what multipath fading is all about. And the first concept that generally being discussed in wireless communication is actually known as two-ray model, which is a very famous model where we consider Earth as being a perfect reflector and you have a line of sight. So this is the basic diagram of this that you normally find in any wireless communication book, and you will find it in Rappaport, you will find in Goldsmith's books and things like that. So you have a height of your transmitting antenna, you have your height of your receiving antenna, then you have a path. You also, two-ray model means there is only two copies of the same signal that is being transmitted due to the reflection with the ground, because here we're going to consider Earth as being a perfect reflector and the signal is 180 degree out of phase, sort of. So this signal is actually your reflected signal. This is going to be a line of sight signal. Now, once you start manipulating those equations, and you can Google it, I will be making that derivation process video because it's a long derivation, because that's why I was trying to delay it, but now I have to do it. You will come across with two different equations. The first equation that you will find in any wireless communication book is going to be this. This is known as your line of sight equation. Line of sight distance. So this is actually comprises of your under root ht minus hr squared plus d squared. Just remember that for line of sight is ht minus hr, the height of your transmitting antenna minus height of your receiving antenna squared, plus your distance between your transmitting antenna and your receiving antenna. For your ground reflected wave, that distance would be under root ht plus hr squared plus d squared. Now instead of subtraction, you will have positive. And then in order for you to find out loss propagation, line of sight propagation time delay, just simply divide this equation by speed of light constant, 3 times 10 to the 8 meters per second, and ground reflected 3 times 10 to the 8 meters per second. So ht minus hr squared, that is for your line of sight, and for ground reflected ht plus hr. You will find these equations in any book. Resources are there in this document. The other piece of equation that you need in order to simulate this scenario in GnuRadio is actually going to be your Frisch equation, which is a very common equation that you normally see, where you have your power received divided by power transmit is equals to your gain of your transmitting antenna, gain of your receiving antenna, lambda divided by 4 pi d, everything squared. This is a very common equation which is known as free space path loss equation that you generally find in any textbook, also known as Frisch equation. So how do I simulate this in GnuRadio? Let's do this. Now, in order for me to simulate this, I need certain variables. So let's look at my flow graph first. All right. In GnuRadio, because GnuRadio is GnuRadio, all the blocks are generally made using what do you call C++, but it has a wrapper of Python. So you can call Python as well. So for example, so there is a block import, and you can import two blocks. Import scipy dot constant. Why? Because I need a constant which is speed of light c. I also need a constant for frequency, which is going pi. I also need pi as well, because that is there in my equation as well. So import scipy dot constant. This is, you're importing something from your science Python library. Then you need to import numpy. Just simply write import numpy. That is when you perform these calculations in our GnuRadio flow graph. These are the two variables that you need. Then you need a variable called samp rate. This is a default samp rate. Let's just choose, you can choose any samp rate you want. So in this flow graph, they have chosen the variable of 512 giga samples per second. So this is one of the variable. The other variable that you need is actually your wavelength. Now here comes SciPy dot constant dot c. So we're from my science pi library, we're taking a constant value that is called c. C is 3 times 10 to the 8 meters per second, divided by frequency, that is giving me my wavelength, which is lambda. Lambda is generally is equals to c over f. That's why I'm using SciPy, and then divided by frequency, I will get my wavelength. Now this frequency variable, this is being controlled by this particular range block that is called frequency, and the range for this is from 900 megahertz is your default frequency, and it's going from 1 megahertz all the way up to 6 gigahertz. And this frequency is being called in this signal source block, which is called frequency, because this is what is going to generate that frequency. All right, so once this signal is being generated, now you have a frequency block is down, you have samp rate is down, numpy and SciPy, these things are down. But what about these 4 variables here? So you have your antenna gain of your receiver, that is 1. You have your antenna gain for your transmitting antenna, that is 1. 1 mean is an isotropic reflectors, which means it's equally radiating the energy in all directions. So generally in free space, in two-ray model, we'll consider that our antennas are omnidirectional antennas, unless and until if it's a directional antenna, that's a different story. Generally in our textbooks, it's considered to be a isotropic radiators. Definitely you gotta have an antenna height. So antenna height is this, and the receiver height is this, but we're choosing the same antenna height. I will make the changes once I run the flow graph. I will make the changes and I'll show you the difference that what happens. Generally in two-ray model, your antenna, transmitting antenna is generally higher. Why? Because it's actually a base station, and your receiving antenna is somewhere in Akamura Hata model as well. It's about 2 meters, because generally that's the distance, that's the length, or that's the height of a normal human being. So let's just leave it as 10 meters, 10 meters. Now, once these variables are down, let's discuss this particular variable, line of sight distance and ground reflected distance. This distance and this distance. So we just calculated this based on this formula. Line of sight is going to be under root ht minus hr squared. So let's look at it. So you have numpy dot square root. So from numpy, we're calling it a function called square root, and numpy squared, which are the values which are being squared, is actually ht minus hr. So ht, antenna height transmitter, minus antenna height receiver, as per the formula. Everything is being squared. Now everything is under root, plus you will have a distance, which is numpy squared distance. All right, now distance is also a variable. That variable is being called by this GUI slider, and that distance varies from 10 to 15 kilometers, 10 meters all the way up to 15,000 meters. So this distance is also a variable distance. We can change this using a GUI range slider. Now let's look at this particular variable, which is gr underscore distance. Now gr underscore distance is ht plus hr. Exactly the same thing. Numpy dot square root, then you have a squared, because both of these quantities are being squared. ht, antenna height transmitter, plus antenna height receiver, everything is being squared, plus you have numpy squared distance based on this. So this is your distance. So these two variables are down. So line of sight distance is down, ground reflected distance is down. Now let's go to my delay block. That's where the delay will come in, because based on this distance you will have a delay. So let's look at what my delays are. Now before I even look at into my delay, let's look at the line of sight delay. Line of sight delay, if you were to look at it, is actually line of sight distance, which we just looked at, divided by my speed of light. This is what it is. So line of sight distance is actually this distance, which we already called using this variable, line of sight variable, right here. Let me move this. Okay, move this here, move this here. So this line of sight is actually what? This is this line of sight delay distance, which is this, divided by my speed of light. So this is being called here. That is that distance. All right. Now same thing for your ground reflected distance. If you were to look at it, this is going to be GR distance divided by speed of light as per our equation, which is this. All right, time delay. So once these two things are down, these are just being called here, and line of sight times SAMP rate. Why? Because line of sight delay, because I want to get an integer value, that's why I'm multiplying it that's why I have an int value, and line of sight is just multiplied by your SAMP rate, because I want to see that many samples based on this line of sight delay and ground reflected delay. Same thing here, GR underscore delay, which is exactly the same thing, GR distance divided by speed of light times SAMP, and int because I want to get integer value. All right, so once these two things are down, so you have a signal that is coming in, that is 900 megahertz, which is variable signal. One signal is being delayed with respect to line of sight, one signal is being delayed based on ground reflected. Is going into a throttle block. Definitely when you don't have a physical device that is connected to it, you gotta have a throttle block. Now it's going into a multiply constant block. Let's look at what multiply constant block look like. Now this multiply constant block, if you were to look at it, this is that Frisch equation that we're using. All right, you have your everything is being multiplied by your gain of your transmitting antenna, gain of your receiving antenna. So let's look at it. Antenna gain transmitted multiplied by antenna gain received, num squared, because everything is being squared, divided by wavelength, multiplied by wavelength, divided by 4 pi d. 4 pi d, this is going to be your line of sight distance, which is this. All right, now I hope you're getting it what I'm trying to say here. So this multiply constant block is going to be what? You have a delay which is going to be based on line of sight distance and GR distance. Now let's incorporate this Frisch equation. This Frisch equation will have a transmitting antenna gain, which is there, transmitting receiving antenna gain, everything is being squared, wavelength divided by 4 pi, you have 4 pi, that's why I'm calling numpy dot pi, that's the constant, times it by line of sight distance, that is this distance. So once this is down, you have another multiply constant. Let's just look at it. What is that? Exactly the same thing. Now instead of line of sight distance, you will have GR distance. Now both of these signals, because these are being added together, if you were to look at it, when you look at this signal, these in constructive and destructive, you have to add these two signals together. That's why we have an adder block here. That's why we have both of these signals are going in, both of them are being added together, then this thing is going inside. So it's going to, if both of these signals are constructively added together, you will see a combination of that in this display, and you're also visualizing the actual signal from your line of sight and from your ground reflected signal. Now let's quickly run this simulation. And boom, here we go. So now I know my frequency can be varied from where to where, from 1 to 6 gigahertz, 1 hertz to 6 gigahertz, and you can go up to 900 megahertz. This is the default value. So default value is being set to 900 megahertz. This in green, this is the combined. If they are constructively added together, destructively added together, you will see it in green. You have line of sight, which is in blue, and then you have the ground reflected signal that is given in red. Now let's start changing the distance, because you can go up to 10 meters all the way up to 15 kilometers in distance, in actual distance between your transmitting antenna and between your receiving antenna. So now let's quickly look at it. Let's run this simulation. Let's increase our frequency a little bit. Try increasing a frequency. Let's see, where do I get this? So here we go. Now these signals start coming together, and this is going to be an addition of these two signals in green. Let's see. Here we go. Here we go. Let's see. All right. Let's quickly decrease this. So I'm increasing the frequency. Those calculations are coming up, and then you will see that they should be coming together. So let me just quickly do it. Here we go. Here we go. Let's see. All right. Getting close. So about right here, they are being added together, and then once they are constructively being added, your line of sight and your ground reflected signal, you will see your signal strength is much higher. Now, on the other hand, if I were to lower down my frequency, let's see, where do I get that? Now, this is okay. Let me just increase this a little bit. Okay, let me just decrease this. Okay, here we go. Now, as you can clearly see, when you have your line of sight signal that is in, and you have ground reflected signal that are both of them are 180 degree out of phase, you will get none. Your receiver will not receive any of that signal. So that's the idea behind constructive and destructive interferences. Now, when I start increasing the frequency, and you can clearly see that you start seeing constructive interference happening, and so on. All right, let's just remember this. Where do I have? Let's try something else. Okay, at 400 megahertz or 400 hertz, I would see that my frequency is somewhere around. You can see that it's destructively destroying my received signal. Now, according to this, let's change this. So let's change the height of my receiving antenna to be about 2 meters. Let's see if I see any difference. So let's just change this. Antenna height has been changed. Now let's run this simulation again, and let's go to about 400 hertz. Let's just quickly go there. Now, see, by changing the antenna, the height of your receiving antenna, you will get a totally different distance. Now, let's see. Let's see, where do I get this destructive or constructive interference? Do I get any closer value to get my? Okay, let's see. Okay. All right. Let's see if it's happening or not. That's the closest that I can go when I have my antenna. Oh, here we go. Here we go. Here we go. So if I have an antenna height, so at the stream, I'm about what 1.4 gigahertz or something like that. This is where I'm getting my constructive interference, where you have your line of sight signal and your ground reflected signal are exactly on the same phase, and you're getting your signal strength almost double what is being transmitted from your transmitter. So that's the beauty of this. I hope you're understanding what I'm trying to say in this particular tutorial. I came across this amazing tutorial. I hope you understand everything. I will be making the derivation process of those equations which I just showed you. If you have any questions, just leave it in the comment section, and please don't forget to like and subscribe to my channel, and thanks for watching. And this is what I wanted to share with you guys.